Okay, everyone. Good afternoon. Good afternoon once again. So, as you all know, I'll be taking the lectures for Stephen, I think, for the rest of the term while he recovers. So this lecture is going to be on linear algebra. The last lecture will be back to my material again this afternoon, but I'll alternate that in the coming weeks. We'll continue with looking at Fourier series later on this afternoon at 4, I believe. So, in the last few lectures, you've been looking at inner products. Okay. Okay, so Stephen tells me you've done up to the theorem 4.1. So did you just get to that at the end of the last session with you, I believe? Maybe did you discuss the Cauchy-Schwarz inequality much? Did you spend a lot of time with it? No. I'll pick it up from there. So today. So first of all, just remember where we are. We're in a vector space, and what we're studying is these functions which are called inner products. Now, very much the way to think of these is as generalizations or abstractions of what you're much more familiar with is just the regular dot product between Euclidean vectors. Vectors in the vector space R2 or R3. So you're very familiar with that notion of the dot product, which is where you sum the products of corresponding components of a vector. And this gives you information about the length of the vector. So when you take the dot product of a vector itself, a familiar vector from R2 or R3, you get the square of the length of the vector. And using that, you can also obtain a nice formula for the angle between two vectors. The angle between two vectors is, well, the cosine of the angle between two vectors is the dot product between the two vectors divided by the product of the vectors' magnitudes. What inner products do is allow us to generalize those notions and kind of operate those notions in any kind of vector space. So an inner product for us is a function of two variables on the vector space. So when he says it's a function phi from V cross V to R, this means the function phi takes two inputs, both from the vector space V, the Cartesian product V times V there, and it takes values, okay, well, it's indicated there, it's taking values in the real numbers. More generally, it will take values in whatever the field is for the vector space. Because you can have vector spaces where the scalars come from a field which is different to the real numbers. It could be the complex numbers or other more abstract fields. And it's not just any old function of two vector variables to the real numbers that we're considering. It's functions that satisfy these three properties. Okay? First property says that it's linear in the first variable, because when the first variable is a linear combination of two vectors u and v, so AU plus BV, the second vector is just a plain old, second argument is just a plain old vector W, then the linear product itself, the inner product itself breaks up as a linear combination of the individual inner products, phi of u with W, phi of v with W. The second property says that the inner product is symmetric, meaning it doesn't matter how you order the inputs u and v, you will always get the same answer. And that's when you combine that with the first property, that says that it is linear in both variables. Okay? So the second property says it doesn't matter in what order you take the variables, And then the first property says it's linear in the first variable, but then you can just flip everything around, and that first variable will say that the first axiom or condition will say it's linear in the second variable as well. The third property is called the positive definite property. It says the inner product of any vector with itself is non-negative, greater than or equal to 0, and the only time it can actually take the value 0, only in one case, when u is the 0 vector itself. Okay? So the 0 vector has an inner product of 0 with itself. Every other non-zero vector has a strictly positive inner product with itself. Okay? So initially we looked at, or you looked at the definition of this, and then you looked at lots of examples. And hand in hand with discussing inner products, we also discussed the notion of a norm. Okay? So just as the length of a vector, what you're familiar with as the length of a 2 or 3-dimensional vector, was the square root of the dot product of the vector with itself, we have exactly the same definition for what we call the norm of a vector with respect to a certain inner product. The norm of V is the square root of the inner product of V with itself. So these things we think of as these are generalizations of the concept of length of a vector. Okay? So we can introduce length-like measures of vectors even in vector spaces where there's no readily available, direct geometric interpretation of the meaning of the vectors. Okay? When you talk about standard vectors in 2-dimensional or 3-dimensional space, you can think of those vectors as being position vectors of points in 2 or 3-dimensional Euclidean space. So the natural immediate notion of length there. But when you're in more general vector spaces of functions, or vector spaces of matrices, vector spaces of other things, where there might not be an immediate, clear geometric interpretation of the thing, well, we can still introduce notions like length and notions like angle between vectors, and still kind of construct a kind of a geometric interpretation for those things, even though it's not one that's kind of readily visible to us as a physical space. So we often talk about inner products and norms kind of in the same breath. So what you've done with this already is you've been familiarizing yourself with the definition. You've looked at lots of examples. So these first examples you looked at were various kind of standard vector spaces, Euclidean vector space. So this is the dot product you're seeing at the top, the dot product in n-dimensional space. The dot product kind of as appropriate for vector spaces over the complex numbers. So there you're not taking the product of components, but the product of the component of the first vector with the complex conjugate of the second vector. That's the natural thing to do when there are complex numbers involved. When you've got complex vector spaces of functions defined on a certain interval, the natural or standard inner product is this, which is very much the continuous version of the dot product, so it's the integral of the product of the functions. On spaces of matrices, the most natural inner product to have is taking the trace of the product of transpose of V on the left multiplied by the matrix A on the right. Okay. The trace of a matrix is the sum of the diagonal entries. So you looked at a bunch of examples, looked at calculating norms, and some of the exercises, the initial end of chapter exercises that are in the book, are a lot of exercises with working the definition, meaning when you're confronted with various candidate functions, various 2-variable functions from a vector space to its scalar field, normally the real numbers, testing whether or not those candidate functions are or are not inner products. That's very much the kind of skills you want to have to be able to work the definition in that way. So I know with my own group, we did some of these examples in our last tutorial. You may have done them recently or be about to do them in the tutorial this week, where you see here in questions 1, 2, and 3, you're confronted with various 2-variable functions on a vector space to the field of scalars, and it's the same basic question. Each of them, is it an inner product or is it not? Okay. And there you're very much what you're doing, just like with the definition of a vector space and with the definition of a linear transformation, you're either trying to prove that the conditions are all satisfied, in which case you need a general argument, which is applicable to every possible pair of vectors and every possible scalars. Or you're looking to discover an example, a counterexample. If it's not going to be an inner product, you want to exhibit or point out very clearly one instance where one of those properties fails. If you can do that, then you prove it's not an inner product. Because the inner product has to always satisfy these properties for any choices of vectors u, v, w, and any scalars a and b. Okay, so inner products can be very diverse. Even on the same vector space, you can have many different inner products. But there are certain kind of fundamental things that always hold. And we can always define, so what we've seen already is we can always define this length-like measure called a norm by taking the square root of the inner product of the vector itself. And the Cauchy-Schwarz inequality is another example of something that's fundamentally true about all inner products. Okay. Now I don't think Stephen showed you a proof of this. So this Cauchy-Schwarz inequality, I won't go through the proof of it now, but I may do it in the next lecture for that. So this can be proved from those three properties, from the three conditions in the definition. And along the way, what you also make use of, one way to prove it, and I'll show you this next time, I think, along the way, proving the generalization of Pythagoras' theorem. So Pythagoras' theorem, just on a triangle, you know as a relationship between the three sides of a right-angled triangle. So it's the sum of the squares of the lengths of the two short sides is the square of the length of the long side, the hypotenuse. That has a generalization to a statement about norms and inner products in general. Okay? And the usual way of proving the Cauchy-Schwarz inequality proves Pythagoras' theorem first for general inner products. Okay? So I might show you that next time. But yeah, maybe we'll work through a few examples here using these notions of the Cauchy-Schwarz inequality and some other things to do with orthogonality and angle as well. Okay? So just as we had the definition, of angle, what we understand is the regular angle between two vectors using the dot product, so we can mimic that definition to talk about the angle between vectors with respect to a general inner product. Okay? So even if you're in a vector space where, if you're in a vector space where there isn't an immediate explicit geometric interpretation of the objects as living in a physical space, we can still talk about the notions of angle between them. Because we can mimic the definition of angle using the dot product. Okay? So compare with the usual definition of angle, which is the cosine of the angle theta between two vectors, A and B, is the dot product of A and B divided by the product of the lengths of A and B. So you can see we're just mimicking that, or we're just doing exactly that definition, but instead of talking about the dot product, we're talking about this inner product. Okay? So we got the inner product 5 UV in the numerator, and in the denominator we've got the the products of the norms of u and v. So here, norm, again, the norm of the vector u is the square root of the inner product of u with u, and similarly for the norm of v. If you've got the notion of orthogonal, if you've got the notion of angle between two vectors, you can also talk about the notion of two vectors being perpendicular or orthogonal. So you might talk about two normal geometric vectors as being perpendicular. The angle between them is a right angle, 90 degrees. But if you're speaking in general, in a more general setting with respect to an inner product, we normally prefer the term orthogonal. It's a more kind of general term. So the two vectors are said to be orthogonal, and it's always in brackets with respect to a certain inner product if the inner product of those two vectors is 0. And this corresponds to, of course, the cosine of the angle between them being 0. So therefore, that's taken as being an angle of 90 degrees, or being perpendicular or orthogonal. So as well as a pair of vectors being orthogonal, we can speak of sets of vectors being orthogonal. Well, it's just the generalization from saying a pair is orthogonal to saying a set of n vectors is orthogonal. What that means is that if you select any pair of vectors from the set, any pair of different vectors from the set, they will have an inner product of 0. So here it's saying this set S is orthogonal if the inner product of Vi with Vj, as long as I is different from j, if that inner product is 0. Okay? If I is equal to j, you're looking at the inner product of the vector with itself. So that's the norm of the vector, and that's not going to be 0 unless the vector itself is 0. Typically, we talk about orthogonal sets when we're looking at candidates for a basis for the vector space. Orthogonal is a general condition. A specialization of that is the notion of orthonormal. So orthonormal means orthogonal plus an extra bit. The extra bit is that, okay, not only are the vectors orthogonal, meaning the inner product of any two different ones is 0, but if you take the inner product of any vector with itself, so this is when I is equal to j, the inner product of any vector with itself is just equal to 1. So when you take the square root of that, you get the norm of the vector. So that's saying that the vector has norm 1. Okay, so that's the normal aspect of it. Building in the word normal. So this normal is equal to orthogonal, an orthogonal family, and all of norm 1. Because if you just say the set of vectors is orthogonal, you're not making any statement or any extra condition about the norms or lengths of the vectors. Okay, so that's some terminology involved here. So there's a bunch of exercises here which we'll talk through, which you'll kind of see various of these definitions being worked and calculations with them. So please do stop me at any time if anything's unclear, you want to clarify. Are there any questions at the moment, or anybody would like to ask? What you'll also notice in these examples is each time we're in a different context. So we're hopping around from vector space to vector space to see these ideas being applied in many different contexts. And that's like an underlying theme here to the whole of the linear algebra half is you're developing a theory of this vector space structure that's applicable to lots of different, real mathematical objects, be they geometric vectors, position vectors of points in physical space, vector spaces of functions, vector spaces of matrices, so on. Okay, so a wide amount of settings. Okay, so well, I don't know if there's much. Some of these examples there mightn't be much to sketch out apart from what's in the notes. So in this exercise here, where you're asked to normalize normalize the vectors u and v. Now, where are u and v here? U and v are in V4R. Okay, Euclidean, four-dimensional Euclidean vector space, standard real vector space. And now normalize, that would mean make them have, rescale them to have length 1, to have norm 1, I should say. So the short vectors you want to stretch out, and the large vectors you want to shrink back, keeping them pointing in the same direction, but rescale them so that they have norm 1. Rescaling, of course, means performing a scalar multiplication of it. If you perform a scalar multiplication of a vector, if you multiply a vector by a scalar, it's still pointing in the same direction, or in exactly the opposite direction if the scalar is negative. You flip the direction it's pointing in. But take that to mean the same direction. It's still pointing along the same line. But multiplying by a scalar changes its length. Now you'll notice here it's using the language of norms and so on, but it's not telling you what the inner product is. So if it's not specifying an inner product, then you should default back to whatever the appropriate standard inner product is for that space. So if this is just a normal Euclidean vector space, then the standard inner product is the dot product. Okay? So the standard inner product here, standard inner product is the dot product, the four-dimensional dot product, which is like the three-dimensional or two-dimensional dot product, except you've got 4 components to sum it. Okay, so it's the sum of the products of corresponding components of the two vectors. Okay, so I'm using that then. Indeed, the norm of the vector x with respect to this standard inner product would just be the square root of the dot product of the vector itself. Okay. This is our usual notion of geometric length. It's the square root of the sum of the squares of the displacements along mutually orthogonal directions. So, okay, coming back to the particular exercise here, given vectors u and v. So if you look at u, you're taking the norm of u, which is the dot product of the vector u itself, and taking the square root of that dot product value. So you're taking the square root of the sum of the squares of the components. So it's 1 plus 9 plus 16 plus 4. That comes to 30. 30 is 2 by 3 by 5, so you can't really simplify the square root any. Just leave it as square root of 30. So this is a largish number, bigger than 1. So you've got a vector, the vector u is norm greater than 1, so you want to shrink it back a bit to make it have length. You shrink it back by exactly 1 over by the multiple, by the proportion 1 over the square root of 30. Okay. So this means it's traditional to put a hat, or this is the caret symbol. You can kind of upside down V symbol. This is kind of typographically called a caret, but if you're reading mathematics out loud, you don't say u caret. It's traditional to read that as u hat. U hat. So we would say the normalized vector u hat pointing in the same direction as u is given by, well, it has components 1 over root 30 by 1, 3, minus 4, and 2, respectively. And if you took the norm of this u hat, well, by definition, it's the square root of u hat dot u hat. Well, that's by definition, see, each u hat is 1 over the square root of 30 times u. So that by definition is the square root of 1 over 30, 1 over root 30 by the dot product of u with u. Remember, scalars, if you have a scalar multiple on one of the arguments to a dot product, or indeed an inner product, that scalar can come out. That's because of the first condition of linearity. Second condition, symmetry, means it's linear in both variables. So there's a factor of 1 over root 13 there, and 1 over root 13 there, so they both come out. So that's 1 over 30, and it's under square root sign, so that comes out as 1 over the square root of 30. And you're left with the square root of the dot product of u with u, but of course we've already worked that out to be root 30, so of course you get 1, as expected. Okay, because the claim was that this normalized vector u hat had norm 1, and indeed it does. I mean, that was just like a check or a proof, if you like, that that operation of dividing it by its norm produces a vector which now has. So essentially, I mean, the things that are being used there, I mean, the reason this is true is because of the linearity of the inner product. That's what's allowing you to take the scalar multiple out of the vector in each position. And then you've got the magnitude divided by the magnitude, so you get 1. Exactly the same thing is done for the vector b. Same operation, just with different numbers. Root 66. It's a bit of a joke, isn't it? Root 66. Rather playing on the music. Anyway, root 66, and that doesn't simplify either. So you're rescaling the vector b by 1 over root 66. Okay, any queries about that? Now that's relatively familiar feeling because it's in 4 dimensions. Okay, that's not familiar, but it's not that far away from our normal 3 dimensions. And the inner product that we're using is just the dot product. So this is the most natural notion of physical length in 4 dimensions. If you were to grant the reality of 4 dimensions, that would be the length of these things in 4 dimensions. Okay, jumping across to look at the next exercise. Now this should remind you of what I was talking to you about at 11 o'clock this week. This is to do with Fourier series, really. Remember I claimed in the introduction that family of basis functions, the constant function, all those cosine functions and sine functions, were actually an orthogonal set with respect to the standard inner product. Well, here you've got exactly this. Well, one instance. So taking the basic cosine and sine functions of period 2 pi, cosine of t and sine of t. Okay, so this is asking us to observe that they're orthogonal over the integral. Again, there's no inner product explicitly stated, so we should adopt the standard inner product here. So the standard inner product for here, again, see he's on the integral, this is phi of 2 functions f and g is going to be the integral from minus pi to pi f of t times g of t dt. Very much continuization of the continuous version of the dot product. Okay, so do cosine and sine behave like this? If you take their inner product, do you get 0? So we can test it out, okay? So the integral we're looking at is the integral from minus pi to pi of the product cosine of t times sine of t. And now that's an awkward looking integral, so it's a product of 2 different functions. A product of 2 different functions of t. One way to achieve this integral, or to carry out the evaluation, is to use the double angle formula, which is a half of sine of 2t is equal to that product, cosine of t times sine of 2t. Then we can make use of just the standard integral So standard result about the integral of sine. The integral of the sine function is minus cosine. And you've got to compensate for the presence of this 2 here. I'm using the chain rule of differentiation. You end up with minus a quarter times the cosine of 2t. And we're integrating from minus pi to pi. So we're going to be evaluating cosine at 2 times pi and cosine at minus 2 times pi. So both of those are equal to 1. So both of these evaluations of cosine are 1. So you've basically just got minus a quarter and minus a quarter. So it's minus a quarter plus a quarter. So it does indeed come out at 0. Okay. So that shows that cosine of t and sine of t are both orthogonal functions. And actually, can generalize this. And we'll probably do a few examples of this in the Fourier series lectures. And generalize this to the inner product of cosine of nt with sine of mt. Any choice of n and m will always lead to orthogonality here, lead to 0 inner product. And also, not only that, but if you take any 2 cosine functions, even if you take 2 cosines but with different n and m there, that's going to be equal to 0 if n is not equal to m. So if they're different functions, those frequency terms n and m there are different, they're going to be orthogonal as well. And the similar thing, but with sine. Sine of nt with sine of n. That will be 0 as well, as long as those frequency terms n and m are different. Of course, if the n was equal to m, this would be the inner product of the function with itself. That would be the square of the magnitude of the function. So that wouldn't be 0, because it's only 0 when you're looking at the 0 function. Whatever it is, cosine is certainly not the 0 function. Now, this next question is interesting. So this is where we're returning. Are any questions so far? Any curious? Is this how Stephen? Does Stephen normally just talk, especially these ones that are all worked out here? Does he? No, does he go through them by hand? Develop them by hand? Okay, even though the answers are already all down there. Okay. Okay. Well, all these ones seem to have answers, but okay. I'll try and bring next time. I'll try and bring questions without solutions here, so we can do a bit more active work. Well, let's see what's going on here in exercise 5. Okay, it's an application of the Cauchy-Schwarz inequality. But what's being achieved here is it's being used here to, not quite to estimate an integral, but to bound or control an integral. And this is an interesting notion. I mean, when you're looking at various modeling exercises, various applications, it's not always necessary to explicitly evaluate everything in sight. Every integral you encounter or every differential equation you encounter, it isn't always necessary to explicitly solve the thing or exactly evaluate the thing. Especially when these integrals occur as kind of error terms or, notions to do with an approximation. Very often, all we want to be able to do is just to estimate their signs or to get some, quantity which is a upper bound for their signs. Knowing the worst case situation, knowing the worst case that quantity can very often be enough to proceed with your argument and get the conclusions you want. So here we're faced with the integral of the square root of 1 plus t squared. from 0 to 1. Now that is a non-trivial integral to do, okay? You can't just, use basic properties of polynomials and that to evaluate it exactly. It's not a straightforward paper and pencil calculation. You probably can make sense of it using some kind of trigonometric approximations. You replace t with cosine t, maybe tan t or something like that. I'm sure there's a way to work it using trigonometric functions. Well, what we're going to see here is not a way to evaluate the integral, but a way to obtain an upper bound on it. Okay? So we're wondering how bad can this value get, this integral from 0 to 1 and the square root of 1 and t squared? Well, by applying Cauchy-Schwarz inequality, apparently we can place an upper bound of the square root of 4 over 3. Okay? Just a number a little bit bigger than 1. Okay? Now, okay, how is this anything to do with the Cauchy-Schwarz inequality? It's about integrals. But the Cauchy-Schwarz, an integral is an inner product on a vector space of functions. Okay? So you just have to look at this initial integral that you're looking at and interpret it as an inner product. Okay? So remember, inner product on function space, standard inner product on function space, function space of integrable functions 0, 1 is phi of f with g is the integral from 0 to 1 of the product of f and g. Now, the Cauchy-Schwarz inequality is replicated for us here. The square of the inner product of u and v is bounded above by the products of the squares of the norms of u and v. Another way to think of these two terms on the right-hand side is that's the square of u, the square of the norm of u times the square of the norm of v. This one on the left isn't a norm because it's an inner product of u with a different value. Yeah. So the thing to do is to look at our integral and think of how we can express our integral in this form here on the left-hand side. Well, the way to do that is to think of it as the inner product of a fairly simple function, the constant function 1, with this other term, the square root of 1 plus t squared. Okay, that inner product is exactly that integral. Okay, the inner product of these two functions is the integral from 0 to 1, so that's the integral we're focusing on, of the product of those two functions. So that's the integral we're faced with. Now we're applying the Cauchy-Schwarz inequality. So the Cauchy-Schwarz inequality deals with the square of that quantity. So this is exactly the integral we're focused on squared. And now we get the simplification happening. Cauchy-Schwarz inequality says we can pass to the inner product of u with u. So u is the constant function 1. v of t is the function square root of 1 plus t squared. So we can pass to the product of the inner product of u with u, so that's the integral of 1, times the inner product of v with v. So square root of 1 plus t squared multiplied by square root of 1 plus t squared. So that simplifies to 1 plus t squared. And that's the kind of magic simplification. That's the useful simplification. Because the awkwardness of that original integral is because of the presence of the square root. If the square root wasn't there, if you were just looking at the integral of 1 plus t squared, there'd be no bother. The integral of 1 plus t squared is t plus whatever, t cubed over 3. It's no problem to integrate. It's the presence of the square root that makes it awkward. But the Cauchy-Schwarz inequality allows you to get rid of that because you're looking at the inner product of v with v. So you're squaring the function v to the complication of the square root disappears. Now you're no longer dealing with the exact value. You're only dealing with an upper bound. But as I said, depending on the application, an upper bound may be enough information to to do something good with it. So this product here, so we've now passed to the right-hand side of the vector sports inequality. These are readily doable integrals. Well, the integral of 1 from 0 to 1 is just 1. And the integral from 1 plus t squared, so it's t plus t cubed over 3, evaluating 0 and 1 is 4/3. Okay. So 4/3 is an upper bound for the square of this inner product, i.e. for the square of the integral that we're interested in. So that means the square root of 4/3 must be an upper bound for the integral that we're interested in. Okay. So this is the integral boundary in absolute value. And that's just one example, but in certain situations, just having a good enough bound or a knowledge of how bad the integral could be is enough to make progress. Okay, so I think there are other similar exercises in the end of chapter exercises about replicating that argument to other Exercise 6 then hops us to completely different context again. We're not geometric vectors now, we're not vector space of functions now, but we're now looking at vector space of matrices. So to remember the inner product here, vector space of matrices. Vector space of matrices of a certain fixed size, the standard inner product is phi of two matrices A, B. This is the trace of B transpose times A. Now, actually, I was introducing this term, an orthogonal matrix. I don't think he's quite, I'm not sure if he's defined that yet. Although I think he does define it on the following page. Yeah. Does he define it on page 31?
Yeah.
Well, that's for two vectors being orthogonal to each other, which is slightly different from just this. Oh, sorry, it's not that use of the word. Sorry, it's this use of the word orthogonal. Okay, sorry. Yeah, in part 1, that's the use on page 31. The inner product of matrix P with Q. Sorry, what I meant to say was this one. So if he just says a matrix on its own is orthogonal, so where's the other thing? So this isn't exactly the use of the same use of the term. What this term here means is that P consists of orthogonal, in the way we understand it, orthogonal columns. So the column vectors which go to make up P are orthogonal vectors in how you normally understand that term in relation to the dot product. So it's just a slightly confusing because it's exactly the same term, but when you use it about a pair of vectors, you're meaning the inner product is 0. But here, when you use it just about a matrix on its own, although it's the same word, it's meaning something slightly different. It means the matrix is an assemblage, consists of orthogonal columns. Or equally well, its equivalent condition that the rows are orthogonal as well. So that's an example of like a context-sensitive meaning of the word. The meaning of the word depends on which context it's used. So we'll pick this up and continue with this when I see you next week. There's a few more exercises open up there in the end of chapter exercises. Okay?